All right. Oh, it's loud. Hello. Welcome and good morning to NDC TechTown. I see the room is full except of maybe 3 or 4 seats, so it's excellent. Thank you for your interest in this talk. I'm Andreas Fertig. I work as a trainer and consultant for C++, and occasionally I also act as a speaker. At least I try to. You can judge yourself. And there's always something that goes wrong. So the picture is back. Let's see how we are doing. The topic of the talk today is C++ coroutines from scratch. So the idea is to show you, teach you coroutines, and well, hopefully you go out of this talk thinking they are a real benefit to the language. I'm German, by the way, and my last name might not be the most typical German name. There are others like Müller or Schmidt, but nonetheless, it's a very German word. My last name is Fertig, and despite me being older than 40 years now, I still pronounce my last name wrong. Proper German, it's Fertig, so it's not a hard G at the end, but at the end I will get it, I think. I have a couple of years to live, hopefully. If you translate it to English, it translates to finished, ready, complete, or completed. So it's an excellent name if you're on the team. Everybody thinks everything is finished just because somebody yells your name, which isn't the fact. I recently had my mother's phone to, configure it somehow, and it's set to German. My own phone is set to English, so I did never notice that. But for all the dialogues you have there, it's an iPhone, so it's iOS. Whenever you have to confirm something because you changed something and they ask you, save it or okay, they say fertig. So you have to push the fertig button. It's really nice. I didn't catch a screenshot, so sorry about that. But yeah, it's very common word here. But enough about the German. As you know, I cannot pronounce my last name, so maybe I'm not the best German teacher. So let's try C++ instead. This diagram here shows you a comparison functions versus coroutines. So on the left, you have the control flow of a function. So this is what everybody of you knows to their deepest heart, right? We have a caller that places a call to a function. That means this function becomes alive. It runs either with a single or with an early return, whatever you prefer, multiple returns, doesn't matter. As soon as the function returns, the entire state, the knowledge of this function goes away. You get a result, maybe the function returns void, but whatever was on the stack for this function disappears. We return to the caller can process the result, or is just happy having called this function, and continues its functionality. Very simple, very easy, works for a whole lot of cases. In fact, it worked for 30 plus years for C++ very well, not having coroutines. A potential control flow of a coroutine is the one on the right. So here we have a caller and a potential coroutine. And the caller now can place a call to a coroutine. It's more or less like calling a function, with one very crucial difference. A coroutine can suspend itself and it can be resumed. And that means during that time, it preserves the state where it was left off. And this is the power of coroutines. This is the key here. And for parsing a coroutine, we have two different new keywords. It's co-yield and co-wait. We'll see them later. I only use co-yield here. And we have a third one. That's when you really want to end a coroutine, and this is co-return. So my control flow here is that my caller invokes the coroutine, my coroutine becomes alive, does some work, and then it decides to co-yield. Usually we do that by yielding a value to the caller, but you can also have a void yielding coroutine if you so want. So we're giving back control to the caller continues its task, and at some point it decides to resume the coroutine. So that means my coroutine now gets resumed exactly where it was left off. The entire state is there. It continues its work, it decides to co-yield another value, my caller once again takes control, runs, invokes the coroutine in my example here one final time. The coroutine runs, and at the end it co-returns. That means, like for a function where you return, this coroutine is finished. Whenever you say co-return, you should never invoke this coroutine again. It's undefined behavior. We will dive a little deeper into coroutines, of course, but for now, you can see it like the first call to a coroutine. It's like creating an object with new. So you get back a handle. This is the trick how you can invoke the coroutine or can resume it again and again. And once you say co-return, it's like you've said delete. So your handle is gone away. So no more invoking this coroutine. So these are the two different control flows. And the power of the coroutine simply is that it preserves its state once it got paused. And you can resume it. What are coroutines? Well, the term coroutine itself is well established since it was first coined by Madeline Conway back in 1958. This, what might appear as trickery to the outside, having something, more or less a function, that goes to sleep and gets resumed. This trickery here has a very, very simple way of doing that. And this is, we have two different flavors of coroutines among programming languages in general. We can have stack full coroutines or stack less coroutines. And this full or lessness of the stack means where this data we need to preserve for this coroutine, so its entire state, where is that state saved? And you can either have an implementation which stores all this data on a dedicated stack piece, or you do not use the stack, and that means you use the heap. And this is what C++ does. So whenever you invoke a coroutine for the first time, that means in the background you get a heap allocation. If we do not think about heap allocation, which compilers might do. But this is the general idea. And this is where all this data is stored from a coroutine. We call this the coroutine frame, which contains all the information that this coroutine needs to encapsulate. That are parameters to this coroutine functions, local variables, and the internal state the compiler maintains for us to know where we left off the coroutine and where it needs to be resumed. So what appears to be magic from the outside, you can hand code this. When we are talking about coroutines, one term also pops up, that's cooperative multitasking, because a coroutine doesn't do threading. It decides when to give up control to a caller, and by that you can implement scheduling. But the coroutine itself says when it gives up control. So you never get interrupted, as long as you're not mixing coroutines with multi-threading or concurrency in general. The benefit of coroutines is that it can simplify your code. We can replace some function pointers, aka callbacks, with coroutines and make our control flow easier to read. Parsers especially become much more readable once you start using coroutines. Because of the third point, we do no longer have to maintain the state. This is what a coroutine now does for us. So we can simply code and can read it in the control flow where we are. And we do not have to look up, oh, what's my state currently? And I'm going to the switch block and so forth. So coroutines make your code in general better to read and easier. How can you interact with a coroutine? As I already said, we have 3 new keywords to work with coroutines. Whenever you see such a keyword, you know you're looking at a coroutine. And by that, this function must satisfy a couple of requirements. But first of all, we have the 3 new keywords, co-yield, co-return, co-wait. If you want to know more about why this co-underscore thing, ask me after the talk. It's a long story. Co-yield means it's basically an output action. It's like returning a value from a function. The caller of the coroutine can receive a value back, and the state of the coroutine usually is suspended. Well, as we will later see, it's all up to your implementation what really happens. But for the broader picture, this is how I like to see it. Co-return is also an output action. That means we are returning a value for the final time of this coroutine, and my coroutine ends here. As for regular functions, you can return a value or you can return void at this point. The state of the coroutine after that is ended, so you're not supposed to resume it again. As I already said, that's undefined behavior. The third new keyword, which I haven't used so far, is co-wait, and this is the other way around. So this is an input action. If we are co-waiting in a coroutine, that means the coroutine gets suspended usually, and we are waiting from the input from the outside. So you can see this like passing a parameter to a function, but this time in the middle of a function you pause and wait for the input of this parameter. Okay, so at any point in a coroutine you can say, okay, I need some user input like a yes or no answer, and then I can co-wait that answer and some other task can take over. The elements of a coroutine, so what a coroutine consists of in C++ are basically 2 elements, but they can go up to 4. So the 2 basic things is that in C++ we must have a wrapper type to, well, have an interface into the coroutine. So this wrapper type is the return type of our coroutines functions prototype. And it allows us to control the coroutine from the outside. So we are totally free in what functions to add to this type, how we model it, but the wrapper type must be there. It can also go without any functions. Because the compiler looks into this wrapper type for a definition of another type called promise type, with the exact same spelling as on the slide. And this promise type is a bunch of customization points where you can control your coroutine. And this is what makes coroutines in C++, I would say, at least difficult for beginners, because you have the full flexibility. And the full flexibility means you have to configure it in some way, and that means you have to know a lot, because you need to configure it. This promise type inside my wrapper type can either be a type alias, a type def, or you place the type in form of a struct or class directly in the wrapper type. We will see examples about that later. So these are the 2 basic things we always need. The third one, which you might add depending on what your coroutine does, is an awaitable type. That one comes into play once you're using co-wait. And the fourth component that often also comes with coroutines is an iterator part. Because what coroutines can do is yield value after value. So practically they can model an infinite sequence of data, and that's usually something where we say, oh, we want to iterate over that, or some kind of iterator state. So this is why iterators often come to play here. A coroutine itself, you can see it because it is a finite state machine in the background. It's just that we do not have to hand code it. It's the compiler's implementation, and we just have the customization points in the promise type to fine-tune it. My actual coroutine function, this is the one where I say co-yield, co-wait, or co-return. This is for communication with the outside world. And this function gets transformed by the compiler to match the customization points, or to call the customization points. But we will see examples for that. All right. Good so far? This slide makes me sad. And it's twice as sad because it's my own slide set, right? I shouldn't have a slide in there which makes me sad. But anyways, it's there. So this is a little disclaimer. Please note, for this presentation, I tried to keep the code you will see as simple as possible, focusing on coroutines only. In production code, I hope you believe me that, I work with way more public and private as well as potential getters and setters. But due to screen space and other constraints here, I chose to not go this route. Additionally, I would use way more generic code in production to keep repetitions low, especially with coroutines. I'm not doing this today. I totally ripped out all the generic parts because I want us to focus solely on coroutines, okay? Not to distract you with something where you later ask, oh, is that part of the coroutine? Does that need to be there? Everything is out. Because my goal is to help you understand coroutines, and I'm totally confident that you can improve the code you will see with the usual C++ best practices, okay? That's something I'm confident you can do. That's not a sad part, actually, that's just a disclaimer. The last sentence is the sad part. I also never declare more than one variable per line. I teach that, I do that, believe me. This presentation actually is the only exception so far I know of, and the other instances I gave that talk. Once again, constraints in screen space. So I apologize for that. But now let's look at a coroutine, C++. A coroutine chat. So it's a chatty coroutine. If you look here at A in line number 1, we can see we have a function fun here. And fun returns a type called chat. We don't know anything about that type yet, but if we start looking into the body of fun, we can see a co-yield. So that's enough. We can read further down and see co-wait and co-return, but the co-yield here is enough to know this must be a coroutine. And by that, we now know that chat is a wrapper type. So inside chat, the compiler must find a promise type, otherwise that thing wouldn't compile. So we know that already, still without knowing much about chat itself. If you look at B here, we can see I say co-yield and I'm yielding the stud string S. And then in C, my coroutine uses co-wait and it awaits a stud string object. So because in the background we will see it's just about invoking functions, I need something here to trigger the machinery in the background. So I'm using a default constructed stud string object for this co-wait. I will receive a stud string and see out that here in C. And then finally, the last step in the coroutine in D, I say co-return and I return the string here. Okay, very simple. I also annotated here, when I say co-yield, that means in the promise type you will find a function yield value which gets called. If we say co-wait, we will find a function called await transform inside our promise type. And for coroutine, for co-return, there is a return value customization point. We will see them next, but this is where the compiler does rewrite our function. The using part here below in use, in E, I call fun for the first time. That is like for object creation when I'm calling the constructor of an object. With new maybe because I'm getting back something like a handle. And I'm storing that in form of chat in the object chat. Okay, so this is the first step. Coroutine got invoked the first time, became alive. In F now, we can see I'm calling chat.listen. I know I haven't shown you the definition of chat, but you now know it comes at least with a member function listen. That's supposed to return something that can be couted. And then in G, I call chat.answer, passing a stud string to that member function. And finally, in H, I call chat.listen again. If you run this code with the rest that we will see on the next slide, that means that the control flow is roughly that the coroutine says, hello, and then my use function asks, where are you? And the coroutine replies, here. So it's a chat, right? Now if you look into the mechanics, this is the promise type. And in A you can see two variables in one line. But I decided I wanted to split MSG in and MSG out for more clarity. These are my two member variables here, which I use as storage space. to preserve the information I receive or I should send out. In B, we have our first customization point, unhandled exception. I'm not going to talk about exceptions and coroutines in general today, so this implementation will always remain empty. But you can customize the behavior, what should happen if you encounter an exception inside a coroutine. Okay, it's beneficial and crucial. This would just terminate, yes. Without doing anything, it just terminates. But here you can control that you log more, that you try to keep your program alive, but the coroutine is gone anyways. Let's say it that way. So once you encounter an exception in a coroutine, that coroutine is gone. All you can do is preserve the rest of your program or let everything die. In C, I have the customization point getReturnObject. So the compiler knows that in the return type of the coroutine, the wrapper type chat, there is the promise type. The compiler knows how to construct this promise type, but it doesn't know how to construct the wrapper type. Because you can have a constructor that takes 0 arguments, that takes a bunch of arguments, that takes a single argument like here. So this is our way to teach the compiler how to construct the wrapper type. And in my case, I'm saying, well, I'm passing this pointer of promise type to chat, building the relationship that chat can control the coroutine. The next two customization points are when the coroutine first is created, there is an initial suspension point, at least a possibility. This is initial suspend. There I can control, should this coroutine return or pause better after it's being created, or should it continue directly? As a mental model, you can see it like if you're creating an object and you have a constructor, most of the time you only initialize all the members of the class in your constructor and then return. Means you have a valid object, somebody can work with that. But I've also seen like 1,000 lines in the constructor's body doing some additional work, more or less the entire program, right? So that means the constructor doesn't return immediately because he's had a lot of work to do. And this initial suspend is practically the same thing. If initial suspend says suspend always, that means our coroutine after being created directly suspends. But we can also have it run to its first or last suspension point, whatever we want here. So it's customizable. For yield value, this is being called once we say co-yield. So I take a std string by copy here, I move it into my variable MSG out, and I return a default constructed std suspend always. Suspend always is one new type that we have in the standard library together with suspend never. All they should practically signal is, does the suspension point suspend always or never? We will see an implementation of them later. For yield value, you're totally free in what you want to do here. So yield value can take a reference, a const reference, a pointer, const pointer, and so forth. You have the full bunch available. But it must match what you're co-yielding. And you can also build a coroutine which has different overloads for different usages of yield value, taking a const reference, taking temporary, and so forth. You can try to optimize this here. So this is just a function that a compiler calls, looking before that at the overload set, which one to invoke. Because I have a co-await in here, I implemented await transform, my next customization point. I'm not interested in any data here that I could also transfer during the co-await, so I'm simply taking a std string to have the correct overload invoked, but I'm not looking at the data of this std string. Now inside await transform, I do something that I picked up once I started working with coroutines. I declare this struct directly in await transform. I call that one awaiter. And its purpose is now it basically implements the 3 functions: await ready, await resume, await suspend. So this is what's behind suspend always. So this is my suspension configuration. And for await ready, I say always true. Await resume means it's called once the coroutine gets resumed. So at this point, I need to get a value out, and this is where I'm moving MSG in out. So I'm returning a stud string here, and the wait suspend here takes a coroutine handle. We will see an example of that later. Currently, I'm not interested in storing the handle from the coroutine that paused me, but there are use cases when we want to do that. So that implementation here is empty, and I'm storing a reference to my promise type here to be able to move the MSG in, out in my await resume call. And then in line 22 here, I return a freshly constructed awaiter object passing a reference to this basically. The final two customization points at the bottom of the slide are return value, because I have a co-return in there. This is what a compiler looks for in my promise type, and it's the same as for yield value. You can provide it with different signatures here. So in my case, it simply takes a stud string, but you can also have it take a stud string by reference, const reference, and so forth, same as before. The only difference between yield value and return value is return value does always return void, because it's nothing where the coroutine suspends, and you have the ability to say suspend always or suspend never at this point. So what I'm doing here, I store the received value in MSG out. And my final customization point is final suspend. As for initial suspend, there is one final suspension point where you can say after the return value or after the last suspension point in general, what should be the behavior of the coroutine? Shall it flow to the end of the control flow, or shall it pause there? And the configuration here depends on what you want. Usually if you have a return value there, so co-return, and want to grab that value, you want your coroutine to suspend at a final suspension point. Because if you let it flow to the end, it's destroyed. It's like a auto free if you want. So this is where you can configure that. Here I have my type chat, and well, another thing I'm not very fond of. At the top here, this include should visualize that the code that we just saw goes in this place. Okay, and that's the easiest to visualize that with the include. What I'm doing next here in A, there is a type stud coroutine handle, which is a template, and I type that one with the promise type of my coroutine. And I create myself a shortcut, an alias handle, which I use to declare a member here, mcoro handle. Then I'm implementing a constructor which takes a promise type pointer, and in this stud coroutine handle there is a static member function from promise. You see that in C. So this is asking the internal machinery to convert from a promise type to a coroutine handle. The compiler internally has a mapping table of that. It needs to know that. And with that function, we can invoke intrinsics and get this information. So at this point, I have the handle that belongs to this promise type. Because of this handle situation, this is much like having a pointer in a class. And whenever you have a class that stores a pointer to dynamic memory or anything like that, then you usually do not want the default generated copy constructor, because that would simply duplicate the pointer but not the memory behind it. So this is the same here for the coroutine. We do not want that to be copyable, because then we have two objects pointing to the same coroutine that calls for trouble. So by implementing only the move constructor, in this case, I disable the copy operations, so it's only move constructible here, and I exchange the other side's coroutine handle with a null pointer and receive the coroutine handle from the other side. So it's movable at this point, but not copyable. Again, because of that handle, I have a destructor here in E. That one checks whether the coroutine handle is still valid, and if so, it calls destroy. So it is more or less like delete. And then we see the two member functions we previously saw in the example, listen and answer. Listen here, once again, checks whether the coroutine is done or not. If it's not done, it means we can still use it, so it gets resumed. And after that resume, I use the coroutine handle, and there is a function promise, which brings me to the promise type, and this gives me access to MSG out. So this is how I track the stud string out of the promise type, out of the internal of the coroutine. Okay, so this is directly reaching into the coroutine, tracking that value out. The other way around is answer. That one takes a stud string, and I do the same thing. I use the coroutine handle to get to the promise type, to get access to my stud string MSG in, and I move the just received stud string to MSG in. So this is how I get a value into the promise type, and with that into the coroutine. And after that step, I once again check, is the coroutine still alive, and if so, I resume it. And now it has the value. So this is the implementation for the coroutine chat. In a picture, you can see it like this. On the very left, we have the user-written code in C++. This is what you saw in use before. This is me calling the coroutine fun, calling chat.listen, chat.answer, and listen again. This is regular C++ code. In the middle, we can see chat is my wrapper type. And for this wrapper type, I know inside this wrapper type, I have the promise type, always. Whether this promise type stores additional information, like it did in my case of chat, whether it stores a couple of stud string, a couple of integers, or nothing, that's up to our implementation. The compiler doesn't bother. There are no requirements. My promise type can be totally empty. Okay. The wrapper type itself must contain the promise type. Whether it comes with the function listen and answer, whether you spell it with capital K's or anything else, doesn't matter to the compiler. So it's our implementation. We can also directly reach to the promise type because by exposing the handle as a public member. Okay, we are free to do so. Whether we store the coroutine handle in the wrapper type is our decision. Compiler can live without that. But if we want to reach into the coroutine, we need a coroutine handle. But depending on the implementation, we might not need that. So we have a couple of optional parts in here for my wrapper type. On the right then, we have the compiler implementation. This is my coroutine. You can see in there is the original coroutine code. So this is the implementation of fun. But that one gets heavily transformed by the compiler. I do not plan to show this today, but if you want to head over to C++ Insights, I implemented this transformation. So you can glimpse behind the scenes of a coroutine, and you will see the finite state machine there and how your original function gets transformed. But it's just blowing up, and I think for today it's too much. So that means the compiler here rewrites my code and extracts information like parameters and local variables. They are not ending up on the stack like normally. They are ending up on the coroutine frame. Okay, so this is the trick. Every variable you declare in a coroutine and every parameter you have there, it's not in its usual spot. It's on the coroutine frame. The compiler rewrites your code here. That's the trick. And this is how you preserve all this information, because it's in a storage space that doesn't go away once you return, only if you destroy it. A few definitions before we continue. For the rest of this talk, I will refer to a task as a coroutine that does a job without returning a value. Just has a job. It's a task. I will refer to a generator as a coroutine that does a job and returns a value, either by co-return or co-yield. Right? I promised you to show you also the helper types. So here are they. We have suspend always and suspend never in the standard library. And we saw our customization points, yield value, initial suspend, final suspend, and the co-await or await transform. They all can or have to return one of these customization points, one again. And usually we use the functions in the standard library, but we will also see that I sometimes implement them myself or modify them. The only difference between suspend always and suspend never is practically that suspend always in await ready returns false, and in suspend never it returns true. Okay, so that's the difference. Everything else is empty because it's a default implementation and there's nothing sensible to do here. All right, how are we doing? Are you up for, let's say, another task? Interleaving two stud vector objects. Okay, couldn't that be fun? So I have two stud vectors A and B, and what I want to achieve is that I want to get a value from A, then from B, then from A, then from B, then from A, and so forth. So interleaved. Should one of the two vectors be smaller than the other one, only the other one gets printed out for the rest of the values. Okay, so they do not need to be balanced like I have it here on the slide. How do we do that? Of course, with a coroutine, right? With a couple of coroutines, maybe. That's the fun here. So I have a coroutine interleaved. Why is it a coroutine? Because in line number 4, you can see it comes with a co-yield. Actually, that might be a false positive because that co-yield is inside a lambda. Yeah, lambdas can be coroutines as well. But if you go down, you see in line number 12 another co-yield in the function interleaved itself. So starting at the top, I have the function interleaved that takes two stud vectors of int a and b. And inside my coroutine, I create myself a lambda lamp. That one takes a stud vector of int by reference and returns a generator. The same type, by the way, that my coroutine interleaved returns. So this is the wrapper type. They are obviously the same. My lambda here has a real simple job. It implements a range-based for loop which goes over the stud vector element by element and co-yields that element. So practically every time you call it, it throws out a value of the stud vector. The next one, by the way, so not randomly, just the next one. In line number 7 and 8, I invoke the lambda 2 times, once with the parameter a and the second one with the parameter b, creating myself 2 new coroutine handles, if you so want, x and epsilon. And I can now use them as I do it in line number 10, where you can see this while loop, which checks whether x is not finished or epsilon is not finished. So we are once again looking at member functions of my wrapper type generator. We haven't seen that one yet, but we know it comes with the two functions with the function finished. This while loop construct is something that also occurs quite often in coroutines because they can yield an infinite sequence of data. So if you look, for example, to a network data stream, you can usually not say when it ends. You can say that you want to close the connection, but as long as you're not doing that, data comes in and comes in. In the protocol layer, you might know when a message ended, but you do not know upfront when the data stream will end because the network cable is unplugged, or if nothing happens, it might run for years. So this is why you often have this while constructs or infinite for loops, because some other condition terminates that thing. It's a little ugly and itchy for me coming from the embedded world. That's usually a code smell, having a potentially infinite loop, but with coroutines it's a little different. So in my while loop here, I'm checking whether x or epsilon still has values left. Okay, this is practically the check here. And if so, I'm first processing x, doing the same check again. Is x not finished? Yes, then co-yield the value of x and then resume x. If you look closely, you can see this is the other way around as before. So I'm grabbing a value from the coroutine and then I'm resuming it. It's all configuration. And then I'm doing the same thing for epsilon in the same order. So that means I first get a value from x if one is there, and then one from epsilon is one there. The promise type stores a integer val here. I implement get return object the same way as chat before. I'm passing the this pointer to the constructor. And now look closely, initial suspend this time says suspend never. And this is why I can immediately get a value from the coroutine and then resume it, because initial suspend was passed and the coroutine suspended at a first other suspension point, which is a co-yield. So I let this coroutine run until it got the first value out of this stood vector. And that means I can immediately grab that value and after that resume the coroutine again. Final suspend and yield value return always false, so we want to suspend here, and yield value takes my integer, stores it internally, and returns a default constructed stood always. Because my coroutine only co-yields, I have to implement return void here to signal that this coroutine doesn't return anything should I flow through the end of the function. So should I escape the while loop, there has to be something, it's the implicit return void, and therefore I have this customization point. And as previously, unhandled exception is empty. My wrapper type generator now is the following. I do the same as before. I shortcut my handle, my coroutine handle of the promise type, and I implement a constructor here for my generator taking a promise type pointer. Does the same thing as before, uses the static member function from promise to get to the coroutine handle. It's move constructible only, copy construction is disabled, and I have my destructor in here which takes care of clearing up the coroutine. If it's still alive at this point, I'm destroying it. I have a member function value that uses the coroutine's handle's promise type to get to the value member, get that value out, and I have this additional function finished here, which checks whether my coroutine is already done or not. And I have resume here, which uses finished as the implementation previously. And if it's not finished and I call resume, I call resume on the coroutine handle. So I added a little bit of abstraction here. So this is my generator, my wrapper type. The usage is now the following. I have my two stood vectors, A and B, as they were on the slide. I create a generated G by calling my coroutine interleaved, moving the two stood vectors A and B into the coroutine. And now I have another while loop that calls G.finished and asks whether that returns false. And if so, I'm couting G.value. And after that, I'm calling G.resume. Very nice and easy. Totally ugly is also fair judgment here. That while loop, it's bad. That you have to know in which order to call value and resume. That just calls for long debug sessions, right? So let's add another task. I think there's a plastic surgeon required, not one that tampers with your facial muscles, but some that tampers with our code, because I'm sure we all would like to use a range-based for loop instead of that ugly while loop here, because that would make everything become more beautiful and a lot of questions go away. How do we do that? Simple. We need to add support for a range-based for loop, and we do that by satisfying the iterator concept. So that means my type here must be equal, comparable, incrementable, and dereferenceable. To be precise, it must be not equal comparable, but since C++20 we have the operator rewrites and the inversions, I can stay on the positive side and implement the operator equals equals instead of the not equals. I do that by declaring a sentinel type here in line number 1. It's just a simple tag type. And then I declare my iterator. My iterator stores a coroutine handle. It implements the operator equals equals, and that one takes the sentinel type. It's just to invoke this function, to make this machinery work. We do not want to transfer any data at this point. And my operator equals equals checks or returns the result of the check whether the coroutine is already done or not. Operator plus plus, the pre-increment operator, of course, because I do not pass an empty parameter here. That one resumes the coroutine and returns a reference to the iterator. And then finally, my dereference operator, line number 17, reaches to the promise type via the coroutine handle and therefore the member well and returns the value. So these are the three functions I need. The coroutine itself here has the entire state, so I do not need to spawn off other iterators. I can simply use it like that. And this code here now, you either put it directly in the generator or you add a little bit of generic parts to have one generic iterator and put it somewhere else. Inside my wrapper type generator, I must provide two member functions, begin and end, if I do not want to go for the free functions, of course. Begin here returns my iterator by creating an iterator by passing the coroutine handle, and end here returns my sentinel type. So this is just to have the machinery work, that I have something that I can compare begin and end with. And because my operator equals takes a sentinel type, I can always compare to the end, but the coroutine knows the end. I do not have to pass it in the actual call to end. Usage-wise, I still have my two std vectors A and B. I create my generator G, my coroutine, by calling the coroutine interleaved, moving the two std vectors A and B into the coroutine. And now the nice part is that I have a range-based for loop now where I can iterate over G, grab a value and see out that one. So all the other abstraction is now gone. No need to know whether to call resume or value first. The abstraction does it. So this is how I wanted to present it to my users. The other part was very ugly. All right. We just have time for another task. Scheduling multiple tasks. Isn't that a great task? We don't do too much, only two. So what I want to achieve is, I want to schedule two tasks. And the code should roughly look like this. I have a function use that creates a scheduler object, and it creates two tasks, A and B, and passes the scheduler to these tasks. And then later in line number 8, it invokes schedule on the scheduler, scheduling the two tasks. That's the idea. My two tasks are very simple. They are more or less the same. The only difference is that one says A and the other one says B. So they say, hello from task A. A is back doing work. A is back doing more work. And between these three outputs, they use co-wait to call suspend on the scheduler. So my scheduler obviously comes with a suspend member function. As I said, the two tasks are absolutely identical except for the A and B part. These co-waits here, they are in cooperative multitasking where you give up control, because now another task can run. So you do not get interrupted like in regular concurrency, multithreading, where you have to lock all your data structures against concurrent access. Here you say when you want to give up. That's the beauty. My scheduler implementation uses a std list of coroutine handles of type void. Because I'm not interested in the promise type, I do not want to do anything in particular with this coroutine except for basic functionality, checking whether it's done and resuming it. I'm happy with a void coroutine handle, type erased. In schedule here, I grab the first entry in my list of coroutine handles, check whether this coroutine is done. If not, I resume it, and the result of schedule is to check whether my list of coroutines, my list of tasks, is empty. That's the result of schedule. The implementation of suspend now does something a little bit different than before. I have this awaiter struct here, but this time, just to show you a different approach, I derive from suspend always, the type we have in the standard library, and that should signal what this awaiter does in general. It suspends. and I'm overriding only the additional functions that change. So because of that inheritance, I need a constructor here to initialize my reference to scheduler scat. But the only function I'm overriding from suspend always is await suspend. Remember, await suspend can take a coroutine handle, and this time I'm interested in that coroutine handle because I use await suspend and the coroutine handle I get here to store that coroutine handle in the scheduler. This is why I have the reference here in the task list at the end. So I'm pushing back that coroutine handle to the end of my task list. And this is why this time I'm interested in the coroutine handle once the coroutine gets suspended, because I need a way to resume it. Well, the good thing now is that this wrapper type and the promise type might be the shortest that you can write. That's it. So my wrapper type task here, it's only a vehicle for my promise type. It doesn't come with any additional member functions. It doesn't come with any state. It's totally careless. It's just, hey compiler, I'm the wrapper type, but here's your promise type. You're interested in that one. And my promise type is also quite simple because the wrapper type task is default constructible. Get return object simply returns a default constructed task object. Initial suspend and final suspend this time say never. We saw initial suspend previously saying never, but final suspend this time also says never, because I have no coreturn in this coroutine, and it can or it will flow through the end of the function, and my wrapper type here does not store a handle to the promise type. There's no way to destroying that coroutine, but it needs to be destroyed, right? There's heap memory behind it. So if I say final suspend never, because I do not want to get a value after the final return, the compiler will handle the destruction, because final suspend never means the compiler flows off the end of the entire coroutine, and that means it destroys it itself. So this is the trick here. So this is why in this specific case, final suspend is never. But if you do that and still want to get a value out, you are in trouble because the memory already was deleted. So this is the combination you have to watch out for. As I said, because the coroutine doesn't return anything here, I implement the customization point return void empty. Of course, these are all customization points. Maybe you find for your application something sensible to do here. Maybe you want to lock this state or whatsoever. You can do it here. And unhandled exceptions are also not doing anything. So this is one approach of implementing a very, very basic scheduler using coroutines. There's another one. What if I say, I still want to implement the two tasks, what we just saw, but instead of having to pass the scheduler to the tasks, I make that one a global object because it's a scheduler, it's always there, so maybe that's an okay idea. So task A and B in this example do not take any parameters. We can see I have this G scheduler object here in line number 6, which should indicate that we are looking at a global variable, and that one now calls schedule. With that change, my two tasks, signatures A and B, become different. So they obviously do not take any parameters anymore. And that means they have to do something different for their co-wait because they no longer can reach for the scheduler's co-wait function. Well, it's a global object, so technically they can. But I want to show you a different way here. Co-wait this time creates a default constructed suspend object. This is something I implemented. So this is different. They do not reach for the global object themselves. The implementation of my scheduler here still uses a std list of void coroutine handles. It comes with another member function, this time suspend, which takes a void coroutine handle and pushes that one back to the task list. And schedule is the same implementation as before. Get the first entry from the list, see whether the coroutine is still resumable. If so, resume it, and as a result, return the amount of tasks left in the list. The different part this time is this one here. So first of all, I have my global object static gscheduler here, but I also have the implementation of this struct suspend. And I wanted to show you this because there is another thing we got with coroutines in C++20, and that's another operator. This is the co-wait operator. And this is what suspend here uses. Suspend in line number 4 implements the co-wait operator. Internally, you can see I once again declare this awaiter struct. It derives from suspend always. And this time, the only function I'm overriding is await suspend. It takes a void coroutine handle and it calls gscheduler.suspend, passing the coroutine handle. In line number 10, then, I'm default constructing such an awaiter object and returning that. So my co-wait operator here also returns something like suspend always or suspend never. So this is how you can have something, let's say, more or less unrelated to your original coroutine that still can play together. Okay, it does not have everything to be encoded into your wrapper type or your promise type. You can also split it apart. So this is scheduling tasks with coroutines. Well, what's next? I don't know what's next for you. I hope this talk leaves you in a state where you either say coroutines are a great and beneficial thing to C++, I want to learn more, or maybe you said, well, there was nothing new in this talk for me, I already knew that. Or you say, oh gosh, that guy so scared me away from coroutines. What do I do next? I have an answer for all 3 cases, I believe. It's a single answer, so it's perfect. Tomorrow, same time, but room number +1, if I'm right, room number 4, should it be at the same time? There's a talk by Hannah also about coroutines. And knowing her, I believe it's a very, very great talk. So if I got your interest in coroutines or scared you away, whatever it is, give it another try and watch Hannah's talk. I will be there. So that being said, if you're interested more in coroutines, you can go to my newsletter and grab my coroutine cheat sheet, which, by the way, Hannah helped to bug fix and improve a little. Or you can grab my C++20 book in print or online edition. It comes with coroutines explained and, of course, other C++20 parts. That's it from my side. I'm happy to open the floor for questions. All I have to say is I am fertig. Thank you. Thank you. So are there any questions? I'm not sure if we have a microphone, but I can echo them. Yes?
You said that a coroutine does not have a stack. Or what?
I said that a coroutine does not have a stack, or what? Maybe I said that. So what I meant to say is all the variables, all the parameters that we find in a coroutine, they are not on the stack. They are in a specific heap allocated piece of memory. The coroutine itself gets transformed by the compiler. So in the end, it's a normal function, which is way bigger if you look at the transformation in C++ inside than the original code. It comes with the setup. It comes practically with a big switch case, switching over all your suspension points, figuring the index out, so where you left, index 1, index 2, index 4. So every suspension point practically becomes a number. So this is the trick how you switch back. And this index is also on your heap. The function itself then, that one is on the stack. So, but the usual variables, the usual candidates where we are interested in, they're in this heap segment. So yes, there is some stack involved, but not that much, I would say, and then the vital information is preserved on the heap frame. So it's also not a case that when we leave the coroutine that the stack is moved into this heap. You're always accessing, or all the variables are rerouted to the heap. So there is no copy phase. It's only the usual things that you need for a function call that are on the stack. So the register for the return value for potential parameters and so forth. After the initial setup, so after the first invocation of a coroutine, your subsequent calls will practically call a variation of the coroutine which gets the coroutine frame pointer passed to it. So this is how you can have one coroutine that works with, or is created multiple times. You only have one time the code, but the variable are outsourced in different dynamic memory segments. Does this answer your question? Perfect. Peter.
Do we have a microphone or not?
Yes.
Yeah, we have one.
I think a lot of confusion is the terminology of stackless and stack full. And it is kind of confusing. It confused me a lot. And the stack full coroutines, which are not in C++, are in a way where you, from within a coroutine, you call other functions, and those functions can actually suspend to the original starting function of the original coroutine. In C++, we have stackless, so the suspension only goes one level deep. You cannot go deeper, and that's this kind of confusion that tends to be there. Consider that if you have a DIY threading infrastructure, if you yield a thread, it goes outside wherever other threads are there. With the stackless coroutines, you only can more or less yield to the direct immediate outside, where your, let's say, that magic return type with the handle is actually living. That's where you more or less return to.
Perfect. Thanks. More questions? Yeah, we have one.
I can simplify. But you always mention the things are living in dynamic allocated memory, and I didn't see any customization point where I can get rid of the internal generated new. Where I can find this information I could.
So to rephrase your entire question, because the first part wasn't on the microphone, thank you. You say that you see coroutines in general as a perfect thing for the embedded world, because it helps a lot there, but the one eye with a teardrop is the heap allocation that happens and does not seem to be customizable. That in fact is an issue. You can customize it in. You can overload operator new. Okay. One tricky part is knowing the entire size of the coroutine frame, because that one obviously depends on how many parameters you are passing to the coroutine and how many local variables do you have in the coroutine. So this is nothing that you know in your generator up front. I have a triggerish code snippet from Gore, who was more or less the creator of coroutines in C++. I'm happy to share that with you. They use a two-step approach over Lambda, so it's not necessarily nice or beautiful, but you can make it work. So you can come to a bit more control. And if I'm correct, then we are looking currently into that, but the problem is knowing how large this coroutine frame ends up to at a very, very early stage during compilation. So what you want to, in a perfect world, is having a constant that tells you this coroutine frame is 100 bytes. So then you know your promise type size and so forth, you can calculate that. But you need that at compile time as a constant to allocate a fixed size array thing. So that's the usual. So this is the tricky part even for implementers in compilers to get this value early enough, as far as I understood it. The other thing that I know that a lot of embedded systems do as one escape path is they have an amount of time where dynamic allocations are allowed during boot up. And after that phase, no allocations are allowed anymore. So you set up everything you need up front, assuming knowing that you have enough dynamic memory, and then after that there are no heap allocations anymore. So this is one other way, but both are not perfect. You're welcome. All right, maybe one last question before we close out, if there is still any. All right, perfect. Then thank you very much and enjoy NDC TechTown. Thank you.